Let us start today's class. We stopped at the point where we discussed. We were discussing the propagator of the real scalar field, and we found that we started from this equation, which is basically the Klein-Gordon equation in the presence of a source. So this is the source star, and we wrote down the solution of this equation. The solution turned out to be of the following form. So it is basically given in terms of this function, which is called the Green's function, and the Green's function is given by the following equation. Function which satisfies an equation of this form. The equation of this form is said to be the Green's function for this operator. But this is the Klein-Gordon operator. The function which satisfies this equation is said to be the Green's function for the Klein-Gordon operator. The solution of this equation in this inhomogeneous partial differential equation is given in terms of function, which is the Green's function. And what is phi naught x? Phi naught x is satisfies the homogeneous Klein-Gordon equation. So we discussed this thing, and our aim is to find out the form of this Green's function, and this you can actually find it out by the method of Fourier transform. So we write gx prime in the following form: gp e to the power of minus I p dot x minus x prime. Then write this in this form. And if you substitute this Fourier transform in this Green's function equation, then we found that Gp can be written as 1 by p square minus n square, and that is equal to, you can write this down as p0 square minus omega p square, where omega p square is p square. So this is the thing that we derived in the last class. Remember that the limits of this integration are from minus infinity to plus infinity, and this is the form of the Green function. In this Gp, the Green's function in the momentum space, put it over here to get the Green's function, the position space, in terms of the space-time coordinates. From this expression, we can see that the Green's function has poles at plus minus omega p. So when we substitute this expression over here, we should remember that this d4p, this integration measure that we have here, comprises of d cubed t, the spatial part of the momentum, free momentum, integration over the free momentum coordinates, and the integration over dp0, the zeroth component of the four momentum. And all these integrals are from minus infinity to plus infinity. Let us look at the p0 integral. The p0 integral is over the real line. It is from minus infinity to plus infinity on the real line. And on the real line, there are poles along the line of integration at plus omega p and minus omega p. So this tells us that there is a problem, and we know how to do handle poles. We handle poles by the method of contour integration. We go to the complex plane, complex p0 plane. You can go to the complex p0 plane and do it by the method of complex integration by using Cauchy residue theorem, and that is what we shall do now. But before that, you can see that if this is the p0 line from minus infinity to plus infinity, then and say this is the zero of the p0 axis, and so this is minus omega p, and this is plus omega t. So the poles are at these 2 points. These are the poles. So what we can do, we can choose a contour which actually bypasses the poles like this. We can do that. But we can do another thing without keeping the poles on the real axis. We can push them up and down in the complex plane. And we shall follow that prescription. And that prescription is basically nothing but known as the Feynman's epsilon prescription. So let me tell you what this epsilon prescription is. I find that this is not working today. This is not working. The other side of the board is not working, so I have to restrict myself today on this side. So let us see what the epsilon prescription is. The epsilon prescription is nothing but you replace this GP, the Green's function in position space, in momentum space, by some delta p, which I call delta fp. So this is the Feynman Green's function in the momentum space, and this Green's function is basically given by e square minus n square plus I epsilon, where epsilon is greater than 0. So this is the Feynman epsilon prescription, and this basically tells us that this is P0 square minus omega p square plus I epsilon. Okay? And from here, you can immediately see that you can write this down as 1 by 2 omega p, 1 by 2 omega p, 1 by p0 minus omega p plus I delta minus 1 by p0 plus omega p minus I delta. You can write it's not like this, where delta is once again greater than 0 and it is related to epsilon in some way, and you can find out what is the relation between delta and epsilon. What you need to do is you just simplify this thing. If you simplify this thing, then you will get P0 plus omega p minus I delta minus of P0 minus omega p plus I. Yes. Divided by, this is basically A minus B and this A plus B. So if we multiply, this will be A square minus B square. This is basically P0 square minus omega p minus I delta whole square. This is what it is. From here we find that P0 and P0 cancels. So we find that this is 2 omega p. So 2 omega p and 2 omega p cancels. So what happens is that this 2 omega p, which is better not to cancel this because it will give you a 1. Anyway, let me keep this 2 omega p. So let me do the simplification from here. So this is 1 by 2 omega p, so that will give you a 1 upstairs, and the rest will be minus delta by omega p divided by p0 square minus omega p square minus plus 2I delta omega p. Where what we have done is we have neglected terms of order delta square in the denominator. Just throw it out because epsilon is very small. It is a small positive number. So and from here you can see here also delta is also a small positive number. And delta is actually related to epsilon in the way that 2 delta omega p is basically epsilon. See, epsilon appears here, and therefore 2 delta omega p appears here with the I in front. And therefore, epsilon can be identified with 2 delta omega p. Epsilon is very small positive number, delta is very small positive number. So you can get rid of delta square, throw away delta square in the denominator, and in the limit delta going to 0, this term is also gone. Therefore, you recover back this thing with the identification that epsilon is equal to twice delta omega. Okay? So you can basically write this Feynman's Green's function with the Feynman epsilon prescription, Feynman Green's function in the momentum space in this following way that I've written down. And from here we can immediately see that there are poles at omega p minus I delta and minus omega p plus I delta. So what we have basically done is this pole that we have, which is at omega p on the real line, by the Feynman epsilon prescription, we have shifted this pole downstairs in the lower half of the complex plane, and the pole is now over here. And this pole is omega p minus I delta, where delta is this distance. And this pole is minus omega p plus I delta. Delta is positive, remember. So the pole shifts in the upper half of the plane of the complex plane, and this pole is now at omega p plus I delta. So what this prescription has done is that now you can do the integration on the real line because there are no poles on the real line. The poles have been shifted to the lower half and the upper half of the complex plane. So this is what the Feynman epsilon prescription does. And now what we need to do is to just calculate the residues at those poles to evaluate this integral. So let us do that now. So from here, what we find is, so since we have replaced g of p by delta fp, therefore we must replace g of x minus x prime by delta f x minus x prime. So this is now the Feynman's Green's function in the position space, in the space in terms of in the configuration space, in terms of the space-time coordinates, and that is basically given by integral d4t by 2 pi whole 4. Then we have delta fp e to the power of minus I p log x minus x prime. Okay? And this is nothing but equal to d4t by whole 4 e to the power of divided by delta ft, but delta ft we have just now seen that you can write delta ft in the following way: 1 by 2 omega p times 1 divided by p0 minus omega p plus I delta minus 1 by p0 plus omega p minus I delta. We should remember that at the end of the calculation, what we shall do is we shall take a limit delta going to 0 on the positive side, because delta is a small positive number. So this is what the expression for the Feynman Green's function is. And here, our aim is to calculate at least, you can calculate the full integral, but at least what we now want to do is calculate the P0 integral. And what is that integral? See, before P we can write this down as dqp by whole 4. Then we will have e to the power of, if we break this up, then this will give us a I p vector dot x minus x prime vector. So that is what this thing will give us. And then we will have integral dp0 by 2 omega p. This integral is obviously from minus infinity to plus infinity on the real line, along the real line. And then we will have e to the power of minus I 0. See, P0 you can write on top or downstairs, because we are using the signature mostly negative. So time, if you just move it, it will not give you as minus sign. So you can write P0 anywhere you like. So I'm writing it now downstairs. So P0 times x0 minus x0 x0 x prime 0. That is, so I write it down. And then we have this factor once again. Whatever I have written on top, this start in the bracket, inside the bracket. So our aim here is to compute this integral, this is the P0 integral. Once you compute the P0 integral, you can calculate the P vector, the integration over the 3 momentum also, but we shall not do it now. But what we shall do is we shall calculate this integral. So to do this integral, let us first consider the case where x0 is greater than 0, or rather, let us consider the case where x0 is greater than 0. When x0 is, or in this case, okay, what you can do is, you can actually forget about x prime, okay? Then this will just become delta fx and everything here. So what you can do is just remove this, write this as delta f this, and remove this. That will just make things simpler and nothing else. So this will give ip dot x, and this will be like this. 0 x 0. You could do it by keeping x prime 0 also, but then you need to consider the case x0 minus x prime 0 is greater than 0. But now you just remove all everything and write it simply in terms like this. So this is what your, so this was x minus x prime, this is delta f x. So this is what we have, and let us consider the case where x0 is greater than 0. So if x0 is greater than 0, then you can see that you need to close the integral, close the contour in the lower half plane. Then only the contribution from this semicircular arc will be 0. And if you do that, and in the lower half plane, it basically it will enclose the pole. It will enclose this pole, the pole at omega p minus I delta. The contribution from this pole will be 0. So what we shall have is delta fx will be equal to integral dqp by 2 pi whole 4. Then we have e to the power of I p dot x. Then we have, so, and when the other case is x0 less than 0, x0 less than 0, you have to close the contour in the lower half plane. So what this will give us is the following. The first term will be x0, so this will give us So when you close the contour in the lower half plane, it encloses this pole, and this term will be 0, right? This term will be 0. So what we shall finally have is the following. Since for the first case, for this case, you need to close the contour in the lower half plane, we'll have a minus 2 pi I limit T0 going to omega p minus I delta T0 minus omega p plus I delta times this full thing, right? And obviously we have 2 omega p outside times this full thing. But in this full thing, what we shall have is, and also we have this factor. We need this 2 pi I. I will write it down later. So this will be what? This will be 1 by T0 minus omega p plus I delta. Only this term will contribute. And with this, we obviously have the exponential factor. This we obviously have. Okay. So this is one of the terms. And for this, and for when x0 is less than 0, we need to close in the upper half plane, and then this pole will contribute. For upper half plane, we will have 2 pi I. If you close the contour in the upper half plane, we will have a 2 pi I limit P0 going to minus omega p plus I delta. This will not contribute because this will vanish. This will contribute. So we will have T0 minus omega p plus I delta 1 divided by. I've already taken into account the minus sign. So this will give us P0 minus omega p plus I delta into e to the power of minus I P0 x0. This is what we shall do. So this is the full P integral, the result for the P integral. Right? Is it okay? Are you okay with it?
P0 plus omega minus
P0
P0 second term.
Plus.
second term.
Plus omega. P0 plus omega.
Okay, let me just check. P0 limit P0 omega p. No, for the second term you have to close in the upper half plane. So P0 will be minus omega p because it will enclose that pole.
But sir, that will
P0 plus omega p minus I delta, and this will be also plus omega p. This will be minus I delta. Absolutely. Correct. Is it okay? This is for the first term. P0 going to this. So P0 minus omega p plus I delta and this. And this for the second term, when you close, when x0 is less than 0, so you close in the upper half plane, therefore it encloses the pole at minus omega p plus I delta, and therefore limit P0 going to this, P0 plus omega p minus I delta, and times this factor will contribute, this will not contribute, and you have the exponential. And now it is easy to simplify this full thing that we have now. We need to just simplify it. Okay, if we simplify this, what we shall have is the following: delta fx. From here, we can see that this factor will cancel, this factor will cancel this factor. 2 pi I, we have a minus sign, so I take the minus sign outside, and 1 2 pi will cancel the 2 pi downstairs, and therefore we shall have d cube p by 2 pi whole cube. And what we can do is take this minus sign to the other side and write a plus I on this side. So I is taken care of. We have e to the power of I dot x by 2 omega p. Another thing that I missed is that you should remember that this integral, the value of this integral holds only when theta, when x naught is greater than 0. Therefore, we should put a theta function. Theta x naught we should put here, and the value of the integral when you write it to be this holds only when x naught is less than 0. So we should put minus x0 over here. That's it. Okay. So now we have the following. We have theta x0, and in the limit p0 going to this factor will become e to the power of minus I omega p minus I delta x0, and this factor will become plus theta minus x0 e to the power of minus I p0 goes to minus omega p plus I delta x0. This is the full answer for this, for the p0 integral. And at the end of the calculation, you can take, we have calculated everything. Now you can take the limit, this going to 0 on the positive side. So this term is gone, this term is also gone. So we finally have, this is d cube p by 2 pi whole cube 2 omega p downstairs e to the power of I p dot x theta x0. Then we have e to the power of minus I omega p x0 plus theta of minus x0 e to the power of I plus I omega x. This is the full result. Okay? Is it okay?
Yes, sir.
Good. So now you want to write it down further, you want to simplify it further. So once we have this result, now you can see that you can put this factor here, this e to the power of I p dot x factor here. So this will be I delta f x is equal to integral omega p to the power of. So now you can combine this term with this term and write this as minus I p dot x. Where you should remember, in this case, this is a 4 momentum, and you have combined this term with this term, right? So that will give us a minus, and then this will be plus. Okay. So we have combined this here, but you should now remember that P0 is no longer independent. Okay? P0 is no longer independent, rather P0 is dependent on the 3 momentum P vector by the standard relation, dispersion relation that you have, the relativistic dispersion relation. So here, let me write it down. P mu is basically P0, but P0 is omega P, and this is Pi. Or Pi, you can write it down as P vector. and then we have theta of minus x0, and for this term, you will immediately, it is basically I is omega p x0 plus I p dot x. See, this term you will not be able to combine it as I plus I p dot x, because what is e to the power of plus I p dot x? Plus I p dot x is I omega p x0 into, and this is minus I p vector dot x vector. So you see that there is a sign mismatch. There is a sign mismatch. So for this, you would be very happy to combine it, since this is e to the power minus I p dot x. Therefore, you would be very happy if you can combine this as e to the power of plus I p dot x. That is what we want. But that is not what we are getting, because you see that we have a plus here, but in order to combine it as e to the power of I p dot x, we need a minus here. So there is a problem. But the problem can be solved in the following way. You just make a transformation, p going to minus p. If you make a transformation of p vector going to minus p vector, d cube p under this transformation remains same. D cube minus p going to d cube minus p, that is same as d cube p. Omega p goes to omega minus p, but omega minus p is same as omega p. The only change therefore happens at this level. This also is omega minus p is omega p. P vector going to minus p, so you get a minus sign. You get the required minus sign by making this transformation, everything remains invariant, so that is not a problem. And therefore, this term you can now combine it as I p dot x in a four momentum form. And therefore, the Feynman Green's function, now what you can do is you can change this to x minus x prime, and then what will happen is this will become x minus x prime. So that is why I ignored the x0 prime from the calculation. So at the end of the calculation, you can just incorporate the other point. So what we get from this calculation is that we get the Feynman Green's function in the configuration space in terms of this space-time coordinates. I delta x minus x prime is basically this integral. So this is a very important result. So you can further move on. You can further move on, and you can try to calculate this integral over the three momenta. You can do that calculation. Try this, but we shall not do it now. We don't need to do it at this point. But what we shall find is that this propagator, this Green's function that you have, is actually related to a very well-known quantity that you have already studied earlier in the path integral course. When I taught you path integrals, then you see that you can actually relate this Green's function, or so to say, this called the propagator for the real scalar field. So you can relate this Green's function or the propagator with a very familiar quantity that you already know. So,
sir, the theta function will be changed.
Theta x0 minus x0 prime.
That will be x0.
Correct. When I change this, so this will also be this has to be changed appropriately. So what we will find is theta x prime 0 minus x0. Correct. So you should be careful about the function also. So this is the result that we have for the Green function, for the Feynman Green function. And let us see what quantity this thing is related to. Let us see that. Let us look at the quantity phi of x acting on the vacuum K0, the vacuum of the field theory, of the quantum field theory. So phi of x is the field operator, let it act on the vacuum of the field theory. This you can straightforwardly, it is obvious that this is basically, here you have A and A dagger. A will fill this vacuum, so the only quantity that will be there is A dagger. So you can write this as d cubed p by 2 omega p 2 pi whole cube square root. Okay? And then we have a dagger p get 0. So this is what we shall have. Because a, the other term will kill it, and we will obviously have e to the power of I plus I p dot x. This is obvious. So that brings e to the power of I p dot x, that brings the x dependence over here, and the p is totally integrated out. There is an integration over p. Now, let us take a bra of this equation. If you take a bra of this equation, we get this. Get by bra 0 phi of x. This will be now bra 0. And once again, we will have an integral. So this will be integral d cubed p prime by 2 omega p prime 2 pi whole cube square root, and we will have a of prime. So that is what we shall have, and obviously you will have e to the power of minus I p prime dot x. So this is what we shall have. And now you just change this x to x prime. You just change the x to x prime. To incorporate, see here you have 2 points, x and x prime. So I will write another point here, which is different from x. This point is x prime. Once you have this, let us now calculate 0. Phi of x prime, phi of x. Let's calculate this quantity. This will be integral d cubed p prime d cubed p 2 pi whole cube 2 omega p omega prime. Then we have e to the power of I p minus x. You cannot write it down like this. You have to write it as e to the power of I p dot x minus p prime dot x prime. That is how you have to write this. And then we have 0 a p prime a dagger p get 0. So this quantity therefore is equal to this. Okay. But this, you know very well how to calculate this kind of a vacuum expectation value. Just replace this by a commutator, and the extra piece that you will have will be 0, because the annihilation operator, because A annihilates the vacuum. This can be replaced by the commutator. And you know is delta in P. That is the highest, the bra 0 is the commutator. And commutator, you know, this value is delta P prime P. Okay? And since the vacuum is normalized, therefore get 0 bra 0 is 1. Therefore, this just contributes delta P prime. So if delta P is in this case, okay, this I should be a little bit careful. In this case, you will get a Dirac delta P minus P prime, because we are dealing with the continuous case. In case of the discrete case, it will be a Kronecker delta. In a continuous case, this will be delta P minus P prime. And yeah, in continuum case, sometimes people use this notation also. Instead of a suffix, you just put it as a function, alternative notation. But the thing is that the commutator is a Dirac delta function of momentum in the continuum case. Now, you can, using that, you can actually perform one of the P integrals. If you perform one of the P integrals, what you will get is d cube P by 2 omega P 2 pi whole cubed. Okay. Here also you should remember that P0 is actually dependent on P vector. They are not independent variables. They are dependent by the standard dispersion relation. And therefore what we have is You can write this down as I P dot x minus x prime. Because P prime is equal to P. Since P vector is equal to P prime vector, it contributes only when these are equal. Therefore, at the 4 momentum level also they are equal. Therefore, we can write this down. So what we find is this vacuum expectation value is nothing but this quantity. Is it okay? So this thing is given by this expression, and okay, this is fine. And now you can write down the other expression also, simply by replacing, interchanging x and x prime. So this 0 phi of x prime 0. So what I'm doing is I'm just swapping x and x prime. If you swap that, what you will get is integral dqp, whatever factors you have the same factor downstairs, e to the power of x and x prime has been swapped. So I will get ip minus ip x minus x prime. So when you swap it, this sign just changes. Okay? And therefore, from here you can immediately see the following, that from these two expressions and this expression, the expression that we derived earlier, this expression that we derived earlier, you can immediately see that I delta f x minus x prime is equal to theta x0 minus x prime 0, and then you have this integral, but this integral is nothing but 0 I of x prime 0. Okay? Okay? This plus theta x prime 0 minus x 0, and then you have this integral, and this integral is nothing but this quantity. So this is bra 0 phi of x prime phi of x 0. So the quantity that we calculated earlier, the Feynman-Green's function I delta f x minus x prime, is basically nothing but the theta function times the vacuum expectation value of the product of two operators plus another theta function times this. But this is what? This is by definition is nothing but, you have already learned that this is basically the time order product of phi x prime of two field operators, and you take its vacuum expectation value. Therefore, what we find is that we have this important result that I delta f x minus x prime, which is the Feynman propagator or the Feynman-Green function. This is nothing but the vacuum expectation value of the time order product of two field operators. So this is the central result. So you can actually relate propagators, Feynman propagators or Green's function of the theory, to these correlation functions that we have already discussed in the path integral course. So these are the correlation functions, or these are, we have already seen that these are Green's functions also. So this vacuum expectation value of the time order product of two field operators is nothing but, it is equal to the Feynman propagator, the 2-point Feynman Green's function. So this is one of the important results that you can already derive from by considering free field theories. So this result holds at the level of a free field theory because you have just some free fields, and the quanta of those fields are propagating. They are not interacting with anyone, so they are propagating in space-time. And you calculate the propagator of that field, and the propagator of that real scalar field is basically related to this quantity, to this correlation function. This is a very important result in free field theory, and this result actually you basically find that this result is used or it finds a huge application when you go to interacting field theories. So this is very important result. So we shall stop here now for today. And if you have any question at this point, see here what I've done is I've calculated, I've shown you that this thing is actually equal to this thing in an indirect way. But what you could have done is you could have started from here right away. You could have written down this expression and calculated it independently, and then you would have got this result. You could have done it both ways. So what I would suggest you to do is you start from here, use the definition of time ordering of two field operators, use the definition, apply that definition of this thing, and then you use the modus function and and try to show that it is indeed equal to the quantity, to this quantity that we derived earlier. Okay? So, do you have any questions at this moment? If not, so let us end the discussion here today for the time being. So we shall meet tomorrow at 2:15.